All right, guys, everybody, laptop shut, the usual stuff, right? That's 9 a.m. and let's see.
So we're getting some kind of like feedback in the microphone and the recording side, so you're going to have to wear this one as a backup.
Okay, so does it mean I can...
You can still wear it for the room.
Maybe, is it too loud by any chance?
I think it's okay. I can turn it down.
The feedback maybe because of that?
Well, it sounds like interference.
I see. Okay.
So, and I don't want to take the chance of it cutting out, so.
Thank you.
Yep, you're welcome.
So I'm all equipped. One microphone in each pocket, so this has got to work. All right. So we're going to be, for the next 3 lectures, we're going, next 4 lectures, so next 2 weeks, which is 3 lectures plus 1 guest lecture. We're going to be talking about scanning for patterns, so also known as convolutional neural networks. I have my lecture today. We will have a guest lecture on Wednesday. Be here. This is Scott Feldman and his wonderful work on cascade correlation filters. Oh my, we're down to 10 people today. Okay, so I'm going to have to come up with something clever to make people come. And we'll continue with convolutional neural networks the next week. So in the meantime, I'm also going to be posting a thread later today on Piazza. I'm sure most of you, the quizzes are not meant to punish you over your weekend, right? So I'll open a thread where you're allowed to ask me why a specific question is there, what lesson it's supposed to be teaching you, and I will answer you if I feel so inclined. Okay. All right, let's begin. The story so far, we found MLPs are universal function approximators. They can model pretty much any function. They can be trained through variants of gradient descent. So we're familiar with this. And models that we've seen so far is this simple multi-layer feed-forward network where you have some input going in. This input layer is just the inputs. There are no neurons over here. The input layer feeds to the next layer, which feeds to the next layer, and so on until you get some output. So you can use these to recognize vectors of spectral vectors for speech. You can try to recognize digits, pretty much any other vector data, right? We've seen this. But now I have a new problem. So I have the speech recording. And the speech recording here, this picture here is a spectrogram. You're familiar with this by now. The x-axis is time. The y-axis is frequency. And the color at each point is actually a number which indicates the value of the spectral energy at that frequency at that instant of time. Now it's just a matrix, right? Now the question here is, from this input, can you tell me, for inputs of this kind, can you build me a neural network which detects if the word welcome has occurred in this recording? So, and I'm going to assume that all recordings I give you are exactly the same length, so you can just feed them into whatever network you have. Now if I give you something of this kind, the obvious answer is yes, right? I just plug a network on it, it gives me an output. No big deal. But here's the issue. So I have 2 cases. In one case, the word welcomes occurred here. In the other case, the word welcomes occurred over here. So will a network that has been trained for this one with the welcome up here also give me a 1 if the welcome has been shifted in time? Will it? Mansi? Why not?
It will try to feed in the input and it will get confused because there are 2 of them.
So there's a simple mathematical reason for this. The chalks are all up there, I'm sure. And there's got to be some chalk here. Here. So look at what happens. Think of the whole thing as a vector, right? So in one case, I have some numbers over here, and then I have some numbers over here representing the pattern welcome. In the other case, this is still a vector. So assume these are all 1s for now, and assume these are 0s. In the other case, the location has shifted. So now this is going to look like this, right? The 2 vectors are entirely different. They live in completely different spaces, subspaces. Something that fires on one is not going to fire on the other, right? So Whereas what I want is a simple network that will fire regardless of the location of the word welcome in this recording. And it should not fire if there's no instance of welcome in the recording at all. Same thing with, say, images. Let's say I have pictures of flowers of this kind, where some of them have flowers, some of them don't have flowers, and it should be obvious which ones have flowers and which ones don't. So this doesn't. These arguably may or may not have flowers. Some obviously do have flowers, right? So now the question is, suppose I build an MLP that can actually tell you if a particular image has a flower in it or not. And if that MLP has been trained for this image, is that MLP also going to fire for this one? And the answer again is going to be no, right? Because the patterns live in different subspaces in the two cases. What I want, once again, is a network that will fire regardless of the precise location of the target object. So this kind of problem is very, very, very frequent, right? You have, in many problems, the location of a pattern is not important. The only thing that's important is the presence of the pattern. In both cases, you have a flower. And if you use a conventional MLP which just looks at the image and tells you if there's a flower or not, that thing is sensitive to the precise arrangement of the pattern. If the flower moves from the top left to the bottom right, it's not going to fire. What you want is for the network to fire regardless of the position of the pattern you're looking for. In other words, you want the network to be shift invariant. If the entire pattern shifts, the network should still fire, right? Now, if you have something of this kind, what would same thing with speech, right? So now, here's my problem. Suppose I tell you that I know exactly how wide the word welcome is. That the word welcome, although I'm giving you a 1 second recording, the word welcome is exactly 200 milliseconds long. And then I ask you, is there an instance of the word welcome in this recording? How would you go about it? Say it aloud.
Probably we can break it into 200 seconds frames and kind of see which.
How do you break it? How do you decompose it? Where do you draw your boundaries? You're on the right path, yes.
Scan the record.
You can scan, right? So here's what I can do. I can build a little recorder network which looks for the word welcome and scan. And I can go all the way to the end. I'm going to get one value for every location. And I've basically looked at windows of my input. I've classified individual windows to decide if there's the word welcome in it or not. But I just want one answer. And the one answer is, does this recording have the word welcome? How can I combine these? Who's that it? Shubham? Yeah. OR, right? How do I do an OR over here? The answer is right, but there's a very simple way of doing an OR, in fact. I can just look at the maximum of the outputs, right? If any of these has a 1, has the word welcome in it, it's going to give you an output that's close to 1, and the maximum is going to be close to 1. So if the maximum is close to 1, this recording has the word welcome in it, right? Or I can do something even a little more sophisticated. I could throw in a complete logistic over there, because I would expect that, if I find the word welcome over here, a 1 frame shift is not really going to kill me. So I'd expect that, I'd actually expect to fire for the word welcome in a small sequence of frames as windows. And so having a perceptron of this kind is probably going to give you a more robust answer, as opposed to something that can get fooled if you just have one-off noisy pattern in the middle, right? Or you could do something even more sophisticated. You can actually throw an entire MLP on top of it, right? So in all cases, what we've done is sort of change the problem of finding out if the recording has the word welcome into one of scanning and then combining the outputs. If I were to write some pseudocode, here's what it's going to look like. I'm going to start from t equals 0, slide all the way to the end. At each location, I pull out a segment starting from that location, which is about as wide as I expect the word welcome to be. I put it through my welcome detector. I get one output at each time. I'm going to put the entire lot through my softmax, right? And that's going to tell me if the word welcome occurred or not. And this should give me an answer. And this makes sense, right? There's nothing magical about this at all. It's actually just one giant neural network. Did you observe that? Although I was scanning, the final max or the final soft max is just taking as inputs the output at each location in my scan. So if I just connect the whole thing up, that's one giant neural network, right? There's one restriction though. This neural network is composed of many subnets. And the subnets are these guys, the network that scanned each location. So since you're using the same net to scan each location, if I view the entire thing as one giant neural network, all of these subnets are identical. So this is what we'll call a shared parameter network. So if I were to look at the pseudocode, this entire thing really just represents a single neural network. This is just the final output layer of the neural network, right? So I could just rewrite this like so, giant MLP. Everybody with me? Now, same thing with images. I'm looking for flowers. I could start off with a little network which finds a flower. Then I can scan, right? Start at each location, go all the way from the left to the right. And then at each location, I'm going to get an output. But then if I really want to know if this image has a flower in it or not, I can just put all of those outputs through a max. So each of those dots represents the output at one particular location. So we're going to get one classification output per scan location. You look at the maximum value or maybe put it through a softmax or a perceptron. This is the principle remains exactly the same. And so if I were to write a pseudocode for this, in the case of the image, the only thing that changed is that instead of scanning left to right, I'm actually going to be scanning left to right and top to bottom. At each position, I pull out the segment, I pass it through an MLP, and then I'm going to get one output at each location. I put the combined lot through a softmax, and I get an output. And as before, this is just one giant neural network with common subnets, right? The subnet that looks at each location is exactly the same as the subnet that considers every other location. So this too is just a neural network with that softmax being the output layer. I could write it like so. Everybody with me? Now, given that I've done this, you can ask me the question, where did that original flower detector come from? Where did that original welcome detector come from? Something magical happened when I set the whole thing in this framework, which is that I no longer have to go and train a special welcome detector. I don't actually have to go and train a special flower detector of the right size. All I have to do is to compose this giant network like so and give it lots of examples of pictures with flowers and pictures without flowers, or recordings with the word welcome in it and the recordings without the word welcome in it, and it will automatically figure out. Because you're training the whole thing, it has to know how to fire. It's going to figure out to detect flowers or the word welcome at the right location. And you can see how this should be the case, right? Make sense, right? So the one constraint is that this is what we will call a shared parameter network. What I mean by a shared parameter network is that all of these subnets, they are identical. So also all of the subnets that look at each of these windows, they are identical. So you have a shared parameter network, which means that anytime I train my network using backprop, if I just treat the whole thing as one giant network, if I make an update to this copy, then I must make identical updates to every other copy over here because they're all the same network. They're shared parameter networks. So also over here, in the case of the image, if I make an update to this copy, I must make identical updates to every other copy in the big network. Yeah? And how do we deal with shared parameter networks? It's very simple. Let's take this hypothetical example of a network where I assume that this weight must be identical to this weight. When I speak of shared parameter networks, basically it's a network where I'm arbitrarily deciding that some parameters are going to have the same value. So suppose I decided that these two weights must be the same. Then it's like saying that this weight, Wij(k), is the same as Wlmn, and both of them have the same value Ws, which means that if I perturb Ws, perturbing Ws is going to perturb both of these values. The derivative I'm looking for is how much does perturbing WS change the output and change the loss. And so what I'm trying to be learning is not the individual weights, because I know both of the weights are the same. I'm trying to learn this common value WS. And if you look at the dependence picture, modifying WS is going to modify each of these weights, and each of those in turn is going to modify the divergence. So if I look at the derivative of the divergence with respect to WS, it's going to have two parts, right? You're going to have one line here, the other line here. So it's the derivative of the divergence with respect to this weight times the derivative of this weight with respect to WS, plus the derivative of the divergence with respect to this weight times the derivative of this weight with respect to WS. But we know that both of these guys, all three of these guys are identical. So this derivative is 1 and this derivative is 1. So it just ends up being the sum of the derivatives with respect to each of the terms in the set that are supposed to have the same value. So if I were going to be training my network, which is looking at the pictures, and this network has all of these subnets which are identical, then I'm going to have several parameters which are supposed to be identical. For example, if I was scanning this image, this edge here and this edge here and this edge here must all have the same value. So also this edge here and this edge here and this edge here must all have the same value. So when I'm trying to update their value, I have these sets where I have sets of parameters which are all supposed to have the same value. And so to compute the derivative with respect to the shared value, I'm going to just be summing the derivative with respect to all of the parameters which have that same common value. And so the overall gradient descent algorithm with shared parameters is going to be something like this. For every set S, which has many shared parameters, I'll be computing the derivative of the loss with respect to that common value for the set. And then gradient descent is going to operate on the common value for the set. But then this term, really in turn, because the set includes many parameters, what happened? So this term is going to be, if I expand the computation of the derivative of this one small term out, that one small term itself is going to be looping over all of the parameters, all of the elements in the set which are supposed to have the same value, and I'm going to be summing the divergences with respect to all of those guys. So going back to this figure over here, if I wanted to compute this, the value for this weight, which is going to be the same as the guy here and the guy here because it's the same network scanning, then I would compute the derivative of the divergence with respect to this, plus the derivative of the divergence with respect to this, plus the derivative of the divergence with respect to this, sum them all up. And that sum is what is going to be used to adjust all of the parameters together. So, and this derivative, of course, is going to be computed using backprop. So here's the story so far, what we've seen in the first 10 minutes of class, or first 18 minutes of class. We have, believe it or not, we've just gone through 76 slides in 18 minutes. Position invariant pattern classification can be performed by scanning. And you have 1D scan for sound, 2D scan for images. And you can actually do this in higher dimensions. There's nothing magical about 1 or 2D. These things could be 3-dimensional. You could be scanning in any which way, right? And scanning is equivalent to composing a large network with repeating subnets, which all have the same value. So the large network has shared subnets. And if you want to learn in these networks, backpropagation rules must be modified to combine the gradients from parameters that share the same value. And this principle applies in general to all networks with shared parameters. Questions so far? Yes.
Does this kind of network also work for variant size of the images? Like some images might be so zoomed out or zoomed in, or different resolution, for instance. So does this also work with that? Or do we have
We'll get to that in 2 lectures. But I'll let you think about how you would do that, right? So the short answer is, if I have a network, you could actually sort of scan the same image at different resolutions, right? Scale up and scale down the image and scan it. And you will get an answer, right? But there's a formal way of doing it. Yes?
So the initial motivation that we had to move to this scanning algorithm was that we had one example where the flower was in one corner and we were trying to train it and we said that if it shifts then it won't be able to recognize it. But even here we were sort of resorting to the fact that we need examples where the flower is in different spaces for this to work properly, right? So if we had those same examples in the initial MLP case as well, would that work there?
Because if you were trying to just train one network for flowers in every single position, yes, you could do it, but how many examples would you need? And how big would the network be, right? Here, if I have flowers in 4 positions, I still learn what a flower looks like, and if in the new examples, the flowers are in different positions, I'm still going to find it. Whereas if you did it the way you said it, then every position that I expect to recognize the flower in must be present in my training set. Make sense? Right. Okay. Now, so I'm going to scan this whole thing. Let's just look at this slightly differently, right? So now the entire MLP over here operates when I'm scanning, right? This entire MLP operates on the input one window at a time. So this guy, this neuron, the subnet is going to compute an output at this location first, right? And what happens? First, each of the 4 neurons in the lowest layer are going to compute outputs. Then the 3 neurons in the next layer are going to, the 2 neurons over here in the next layer are going to compute outputs based on the outputs of the 4 neurons in the first layer. And then the neuron in the highest layer is going to compute an output based on the 2 neurons in the second layer, right? So this is the order in which you'll be performing the computation. When you're classifying this block, you'll be first computing these 4 guys. From these 4, you'll be computing these 2, and then you'll be computing the higher one. Oh, shoot, come on. Okay. So, and then when I move forward and I do the same operation on the next block, the same thing happens. I'm going to be computing these 4. From these 4, I compute these 2, and from those 2, I compute that one. And so this is how the computation is going to be proceeding left to right till you get an output at each location, right? That's the order in which we presented it when I think of it as scanning. When I'm scanning with the entire network, I can change the order of operations. So let's say, and that output goes through a softmax. Let's say I just pick that first neuron in the rightmost corner, right? And I individually scan the input for that first neuron in the rightmost corner. And then subsequently, I just compute the neurons 2, 3, and 4 on the first block, and then compute the rest of the output. Is the output in the first location going to change? Anyone? No, nothing happened. All that happened was that I changed the order in which things were being computed, right? The first guy scanned the whole thing instead of waiting for the rest of the neurons to perform their computation. I could do the same thing with the second neuron and right? So I could do the same thing with the second neuron and the third neuron and the fourth neuron. So which means that the 4 neurons in the first layer could just scan the entire input, and then the subsequent neurons could look at each position and compute the output at that location, and the output is still going to be the same. Nothing has changed. And I can do the same thing now with the second layer neurons, right? Each of them can individually now scan the input, and so I can scan the input with the second layer neurons and then look at the output of the second layer neurons in the first position and compute the output for that location, and do the same for the next and so on, and scan and put the whole thing through a softmax. So do you see what happened over here? It's still the same computation. The only thing that changed was that instead of going through it column-wise, we went through it row-wise, right? But otherwise, the computation didn't really change. And so this is still a scanning MLP, a single MLP scanning the entire input. So basically, what we are doing over here is something like this. Let's say this was the original image, original pseudocode. We were going through it left to right, pulling out a segment and computing an MLP on it, and then performing a softmax. Now, let me expand this portion over here, this MLP. I'm going to expand it. What you would do is you are going through the layers. In each layer, you were going through all of the neurons. And for each neuron, you were computing an output, correct? So this was when you were just doing the standards, scanning with the entire MLP, analyzing each location with the entire MLP. All that happened over here was that, now look at those three indices. First, the outermost loop is over time, but then then the inner loops are over layers and over neurons. So at each location in time, you went through all the layers, and in each layer you went through all the neurons. If I change the order of these loops, will the output change? You've written code, right? I can bounce these things around in any which way, and the code will not change. And so this, I can go over the layers first, then I can go over the neurons second. So first I can go over time, and I can go over time for each of the neurons in each layer, and repeat this for each layer. So this is basically what we did in what I showed you in the figure, right? So this is just the reordered scanning with the MLP. And I can write the whole thing in vector notation. When I rewrite it like so, I can say that I'm going to go this inner operation, this thing that goes over all of the neurons in a layer. I can write all of the neurons in one layer as one weights vector, as we're all familiar. And this is just a standard vector notation for the pseudocode in the previous slide. But the concept is clear, correct? I can do the same thing for flowers. So here I want to scan the image for the desired output. And at each location, what we are doing is slicing out that image and putting it through an entire MLP. And so this is what the operation is going to look like. You have the inputs, and then you have one hidden layer, another hidden layer, and then finally the output. If I take a single neuron and then I scan the entire image with that one neuron, like so, right? I'm going to get an output for the neuron for every single location in the image. I get basically a map of the image as computed by that neuron. I can do the same for every one of the neurons in my collection, right? And now, if I want to find out if there is a flower over here or not, all I have to do is to pick those locations from these 4 maps, pass that through the rest of my MLP, and that's going to tell me if there was a flower there or not. Right? Makes sense to everybody? Mansi, you look confused?
Yeah, so in the first neuron, like we decided that we are going like row-wise or column-wise, like in one.
We just scan the entire image with one neuron, right? So it doesn't matter which order you do it. I can actually I can process all the neurons in one location, or I can process all the locations with each of the neurons. It doesn't really matter which order I do it, right? So and then we can recurse the logic. At the next level, I can do the same thing. I can scan these guys and produce a map. And then if I want to find out if there's a flower in this location, all I have to do is to pick this location and the maps of the next layer, pass that through the final perceptron, and it tells me if there's a flower in the location, right? So, and I can compute this for every location in the output in the same way and put that through my max, right? And if I just look at that particular output, that's going to tell me if there's a flower in that specific location or not. So again, what is the actual problem? Is there a flower in the image or not? Not where is the flower. So I can just put that whole lot through my final, whatever, max, softmax, or a full perceptron, right? So I'd be flattening it. All I did was redo the final map into one big vector, and I'm passing it through whatever this final unit is. Here I've drawn an MLP, but it could have been just a single perceptron or a max, right? So this is still the same operation we began looking at 150 slides ago, which is to say you're scanning an input with an MLP. All we did was change the order in which the operations were performed, and the outcome is still just a single MLP, right? It's just an MLP with shared parameters. Nothing is different from where we began.
So what's the benefit of changing the order?
Pardon me?
What's the benefit of changing the order?
let's go through the rest of the lecture. Okay, so here's the pseudocode over here is basically explaining the same thing. Here is what you would do if you were actually scanning things in the usual way and when scanning the entire image with the MLP. But when I change the order, this is what happens, right? All I've done is flip the loops around. Okay, so this is the scanning MLP. And if I do this in vector, I can do the same thing with vector notation. Now this filter, this W over here is going to be one collection of neurons, which is scanning the whole thing and producing a vector output. So now, before I continue, what exactly does an MLP learn? We've seen this in class number 2. The way we did it, we saw that the lowest layers of the network actually capture simple patterns, like they'd be capturing the outlines of these pentagons. The next layer capture more complex patterns. They'd be capturing individual pentagons. The next higher layer capture even more complex patterns. So neural networks, if you want to really make the network nice and parsimonious and simple, you want it to let up build up patterns from bottom to top and not expect everything to be done in just one layer, right? And so as you go through the network, the patterns become more complex. So also if you were trying to find out if these little grids of pixels have digits in them or not, and you trained your network, what you would expect would be that the lowest layer networks find all the patterns that compose digits. The next layer composes the actual digits from them and finds the digits. And the last layer tells you if any of these patterns have actually occurred or not. So the point being that you're sort of building up what you know of the patterns bottom to top. So over here, if I go back here, what does the, wait, is the sound working? I guess so. Okay. So what does this entire behavior look like for the patterns we are looking at? Now, let's say I'm trying to look for flower-like patterns at each location. Then in our standard pattern, standard framework, what we did was to look at this entire block using the MLP, right? So each of these dots has actually looked at the entire block, and subsequent neurons are only sort of combining the information that each of these dots found. But then, what do you think each of these neurons is actually going to find? Each of these neurons is not going to find a flower-sized pattern. More likely, it's going to find something localized. Maybe one of them finds a petal, maybe one of them finds a sepal, maybe another finds some kind of a stem, and then the next layer sort of put these things together to compose flowers, right? So, but then somehow we are sort of collapsing all of this information into just one number, and these guys are just looking at one pixel at a time, right? I can try to make this more explicit. Now, the problem with doing something of this kind is that having a petal in the top left corner and having the same petal in the bottom right corner are being treated as two different things. I would need two neurons, one for the petal in the top left corner, one for the petal in the bottom right corner. But then it's still the same petal, right? So I can recurse the logic, the exact same logic that we did when we scanned the entire image can be recursed to be scanning this block itself for the patterns. Make sense to you guys, right? So what I could do now is to say that within this block within which I'm looking for a flower, I'm going to be looking within smaller blocks, maybe this size. And so when I consider what each of these outputs is, this output is only looking at a much smaller block of the input. And so this is how I'd be scanning, right, like so. Because the smaller block is, the first neuron is looking at small blocks. But then if I want to look at the larger block, what will I do? I'm going to look, the neurons over here are going to look over squares of size 9 in the first block. This should partially answer your question, right? I can keep recursing this logic to make it simpler and simpler. And so, and subsequent neurons, so basically this neuron over here, now observe something that happens. This neuron is going to be looking at the outputs of all of these guys, correct? Which means that it's going to be looking at this block of outputs from this fellow, this block of outputs from this fellow, this block of outputs from this fellow, and this block of outputs from this fellow. because it's trying to get the output of each of these four neurons within the entire block, right? And those are all going in to this dot. So this dot is actually connecting to 9 times 4, 36 inputs. Just to be clear, right? Because this dot is basically looking at, it wants to evaluate this whole thing. This tells you how this guy evaluated this whole block. This tells you how this guy evaluated this whole block, and so on. So that's how the connections are made. And now, eventually this one effectively looks at the entire square, right? And I can pass this on. But then, and what will this find? This kind of analysis is going to be able to tell me that within this block, if the pattern that this fellow is looking for is found to the top left, and if the pattern that this fellow is looking for is found here, and if the pattern that this fellow is looking for is found here, and if the pattern that this fellow is looking for is found here, tell me that it's something that it's flower-like. You can actually begin looking for fairly complicated patterns, which are composed from smaller units, although the smaller units themselves are being scanned for in the entire image. So you can form complex patterns. But then this is still just scanning with a shared parameter MLP, right? Nothing really changed. All I did was I took a step back and began looking for smaller units. But everything else still remains the shared parameter MLP. There's just one minor modification, that if you actually begin looking carefully, then in the first layer, you had these 9, although I'm drawing up an MLP with 3 neurons. This guy, each of these produced, in this case, 9 outputs within this first block, right? And each of these outputs came from a small sub-block. Every line going into any one of these 9 represents all the weights from within the sub-block, and every line represents an identical set of weights compared to every other line going to the same sub-block, right? So that's the only small difference that happened, but it's still the same shared parameter network. And so after that, this is done, the next neuron, if I wanted to just analyze this block, here I'm only showing 3 neurons, then all of these are going to go into each of the 2 neurons in the next block, and those are going to feed to the final output neuron, which tells me if there's a flower in this block or not, right? Now, I can extend this to 3 layers. So I can have the first guy look at really small blocks. I can have the second layer look at sub-blocks of the maps produced by the first neurons in the first layer. And then so this neuron over here looks at this block now. And then I can have the neurons in the final layer look at sub-blocks over here, but that neuron is effectively looking at the entire block, right? What have I done? I've explicitly smeared the information over many layers, so that within each layer I'm scanning for small patterns. I've just sort of, all I'm doing is recursively decomposing the problem of scanning to look for smaller and smaller patterns. I started off by looking for flowers. Yes, Kiran?
I was going to ask, so at what level of granularity do you stop the recursion? Is there a certain bound threshold, let's say 2 by 2 or 3 by 3, where...
We typically stop at about 2 by 2, right? If you go below that, you're looking at scanning individual pixels. Okay, yeah. I mean, they're different, it ends up being problem-based a little bit. You will do this in your homework, you will find out, right? That's the magic answer to everything. You have quizzes and homeworks. Anything that I don't have answers for, you will do on your own. So, and so now this one dot is actually going to scan the entire image, right? That entire block, and I'm now going to be scanning. And the final classification, of course, is going to be looking at this entire lot and putting it through a softmax or a max or an MLP. So again, this is still just one giant shared parameter network. No matter how I'm scanning, the basic fact that scanning and combining the outputs is still just one giant shared parameter network doesn't really change. This is still just one giant shared parameter network, right? So the entire operation can be viewed as a single giant network, but the individual networks are shared parameter sets. So here's some pseudocode which sort of should convince you of why this is the case. Here here's what the basic scanning looks like, right? You're going over the entire image. At each location, you're pulling out a block, and then you're classifying that block and putting all of the outputs through a softmax. So if you look at what's happening within this one over here, you're pulling out the block, and then you're going over the layers, and then you're going over each of the neurons, and then you're performing your affine computation and then putting it through an activation. So I can switch the order of these two blocks, and the computation still remains the same, right? And so when I switch the order for these two blocks, now what happens over here is that the size of the maps basically change for each layer, right? Because each of them can be looking, the first one could be looking at, say, 9 by 9 in the image. The second one could be looking at 2 by 2 in the maps produced by the first layer, and so on. So the width of the block, which is this KL, which is this KL cross KL, is basically just the size of these blocks. So this size is specific to this layer, this size is specific to this layer. That's all they're saying. Okay? Now, I'll let you mull over this in the code. Pseudocode is fairly straightforward. The whole, my point is that I was trying to convey a concept, okay? But then something else that happens over here. Let's take a look at this affine computation. What is this affine computation really doing? So now, this affine computation is this guy. I have this image, and this neuron, let's say, is looking at blocks of this size. The neuron is going to have a certain number of weights, right? So how is the input actually computed? You have the image, which goes from, say, 1 to 3, 1 to 3. The weights, what will the size of the weights be now? The weights are also going to be the same size, correct? It's going to be, say, 1 to 3, 1 to 3. And then you'd be doing a component by component. So this is the image, this is the weight. So you'd be doing a component by component multiplication of these two, and then summing the lot, right? And then you shift one position and repeat the whole operation. And then shift one position and repeat the whole operation. So you're basically computing an inner product between the weights and the input and scanning this left to right. So this operation is what we'll call, what do we call it, guys?
Convolution.
It's a convolution. These are electrical engineers. They know their stuff. These are pre-qualified electrical engineer PhD students. They will not know this stuff after they're qualified. Right? But anyway, so this is just your standard convolution. Actually, this is more like a correlation. Convolutions and correlations are slightly different, but for all practical purposes, for our purpose, this is a convolution. Just in case you missed my words. So this whole operation is now going to be called a convolutional neural network. A convolutional neural network is just nothing but an MLP that's scanning the input for patterns. But you can, typically what we will do is we'll scan the input at finer and finer resolutions as we go through the network, right? So if I did this in vector notation, I'd be going over all of the layers. I'd be going through each of the layers. Each layer is going to have a certain number of neurons, right? And then for each layer, I'm going to be scanning the entire input, right? And while I'm scanning it, I'm going to pull out a block which is the size of the region that's being looked at by the neuron in that layer, and compute the inner product, and then compute the activation, and then finally put everything through a softmax. So does this make sense, right? The entire operation is just a sequence of scans, only because we just sort of reordered operations. Questions, anybody? Right? No.
I have a question.
Yes.
So with those weights, we say it's a 1 by 3 by, or a 3 by 3, I guess.
Uh-huh.
Can it actually be flattened? Because
It doesn't matter, right? It's just a vector operation. Whether you think of it as two squares or two vectors, is the same thing.
so it's more of just a number.
It's a collection of numbers and a collection of numbers. That's about it, right? But we do keep track of the patterns when we scan, because that's what feeds things downstream. You're taking advantage of the arrangement when you distribute stuff, right? Yes.
So here we have already assumed that
No, we have not.
The first part, so we are basically passing the segments, right, to the trained neural network.
We are not, so the point, yeah, here I'm assuming that you have a neural network, but then we mentioned early on in class that you could train the neural network, right? That was something we said in the first 10 minutes of class. Maybe you came in a little late, right? Go back and check. So the point is, this whole thing, nothing has to be trained. I mean, we're not necessarily considering that you need a trained network. This whole process, this whole system can be trained if now all I provide are lots of examples of pictures with flowers and pictures without flowers. And we'll figure everything else out. Yeah, the standard backpropagation will figure everything out. And we'll go over this in the next class. Any more questions? Right. So why do I bother to distribute the pattern over so many layers? Why couldn't I just have, one simple scanning network? What was the benefit of distributing this and saying that, instead of just having this MLP scanning the entire image, why do early layers look at small regions, and then second layer, and then the second layer, why does the second layer look at regions of outputs from the first layer, and so on? This distribution, there must be a purpose to it, right? What is the purpose? So here's what happens. Now this, I'm redrawing things over here. And so this redrawing is, you've got to be careful about it. Okay, first, before I do that, guys, can you put up the URL? Yes. Yeah, just write it on the board. Oops. Write this here. This is for the roll call. So you have 5 minutes to ask questions. Yes?
For each, in the first step for each neuron, we get like kind of an image out of that neuron.
A map, sort of.
Yeah, and for the second layer, so like all these maps are stacked together in
It's looking at all of these maps simultaneously, that's all. Right? Because now look at what's happening here. So this is your URL for enrollment, guys, today. So look at what's happening, right? All of these are being decided to compute, are being utilized to compute the output at each location over here, right? So you're just looking at them because these are 3 different neurons, so you're just looking at all of their outputs. Right? This.
So for example, one neuron in the second layer looks at the map for.
It's going to be looking at regions of the maps for all of the neurons in the first layer. Because every neuron is going to be looking at all the neurons in the previous layer, right? Right. I mean, that's how the MLP operates. Questions? Mia, do you have any questions? No? Okay, so why distribute? As soon as you're done, we will continue. What is the time? I may just run out of time. I'm going a bit too slow. I have 32 minutes, yes. Yes?
So let's say we take this 3x3 things and we jumble up the whole image. It will still say that it's a flower, right? Because the order doesn't matter. If I jumble up all the things.
This is the problem with, okay. Here's the kind of pattern it's going to find. Will jumbling up still work? It's because when this looks at the map of all of these neurons, it might learn to fire, oh shoot, if this one has a high value here, this guy has a high value here, this guy has a high value in the middle, and this guy has a high value at the bottom. So the arrangement actually matters. If you jumbled it, it's not going to find that pattern, is it? Right? So the structure is retained. Okay? So now let me go through this business of y distribute. But then before that, here is a picture that you're going to encounter all over. So this one, let's say I have all of these inputs. In my case, these are vectors, but they could be pixels, they could be numbers, it could be anything, right? And then suppose I'm scanning with, say, a 3 cross 2 cross 1 network, which looks at this much. Suppose I'm scanning like so. What happens is that each of these 3 guys is going to output a value which represents this entire block, correct? So I will redraw it like so. I'm going to, don't go up, redraw it like so. This, instead of having those 3 being drawn horizontally, since all of them represent this block of time, I'm going to draw them like so, as I did when I showed you when I was scanning things, right? And so instead of showing the 3 neurons separately, I can just draw a block. And so look at what's happening over here. Here I have, oh wow. Yes, something was there. Okay, now you know. Oh, wait. So you know, right? All right. So this one actually represents the N1 neurons in this layer, which I've drawn vertically. This, it's going to go into the ceiling. No. Okay. This guy here represents the N2 neurons, which I've drawn vertically up here, right? So this arrow, how many edges would it represent? 3? No? Otherwise, how many? How 4? It's N1 and N2, right? So there are N1 neurons feeding into N2 neurons. So Jacob, how many connections would there be? 8? Where did the number 8 come from? It's N1 and N2. It's got to be N1 times N2, right? So I have N1 neurons here and N2 in the one above, right? It would be 8 for, there's no example on the board that produces the number 8, right? 6 would have been reasonable. Anyway, so, and how about this one? This actually represents how many?
N1 times N2 times N3?
No, this guy, just this guy.
N2 times N3.
N2 times N3, right? So just to give you an idea. Now, each of these neurons is connecting to every one of my inputs. In this case, there are 8 of them. But each of the 8 is a d-dimensional vector, right? And so there's going to be 8 times d connections going into N1 neurons. So 8dN1, and this is N1 connecting to N2, so it's N1, N2 parameters, plus times N2 connecting to N3, it's N2, N3 parameters, and so on. So if I were just scanning with an undistributed, non-distributed network, the actual number of parameters I'm going to have is this, right? You get the idea. Now, if I distribute it, what happens? So when I scan, it's basically the same column scanning through the entire network. So the number of parameters doesn't change because of the fact that I'm scanning. Now, if I begin distributing things, here's what happens. The figure has changed slightly. You may or may not have observed. I have 4 vertical yellow blocks, which is to say there is some, whatever the size, N1 neurons. So this is the same as saying I have these inputs, and I have N1 neurons scanning the input, right? And so at each location, at each position at which they take a snapshot, I get a column. So those yellows represent columns of N1 neurons being taken over, in this figure, 2 inputs at a time, right? The lowermost pattern is scanning 2 inputs at a time. More generally, I'd have some K0 patterns being computed at a time. The second layer is it's like looking at a block of 4 of the guys in the first layer, right? So the second layer, how many total parameters is it going to have? Pardon me?
N2 times N1?
N2 times N1? N2 times K0?
Sorry, L by K0.
This, here I have 4 arrows. Right, it's going to be 4 because each of the 4 is going to be unique. So I have 4 times N1 times N2. Right, makes sense to everybody? And then this upper guy, that's still going to be N2 times N3. And so now if I scan with this figure, this is what the computation is going to look like. But now I have distributed the computations over 2 layers, correct? How many parameters do I have? So here I have 2D times N1 from this first layer, right? I have 4 times N1 times N2 from the second layer, and the rest are the same as before. Make sense to everybody, right? Yes, Jacob?
So if you had to drop out to this, then the network would just be, like, was it 2 to the n of these parameters?
So pretty much, yeah. It's going to be, yeah, but let's not get into that. It's the dropout has to be part of, you've got to consider it in the context of the giant network. It's actually a good question, but yeah. So what has happened over here in this process? In this process, if you compare this number, earlier we had, so observe that the second level neuron is still looking at 8 inputs, correct? But so earlier the number we had was this. We had 8, forget the D, it was 8dn1 plus n1, n2, and so on. Now I have 2dn1 plus 4n1, n2, and so on, okay? The number has changed. But in the process, something has happened. What has happened is that these 2 computations, they are not being performed twice. They're being performed once. The same value is being used both by this guy and this guy. Those things are being reused, right? I can spread this over 2 more layers, over the next layer, right? What is the width of the input that I'm still considering for each classification? Right, Zilly, what's the width of the input I'm considering for a classification over here? Starting from the top, look at the width of the entire tree. How wide is it? 2?
Wait, for the entire tree?
For the entire tree, right? Yes. It's 8, right? Because if I look at how much of the input I'm considering to produce this output at N3, you go down the tree, I'm looking over 8 inputs, right? So in every case we've looked at 8 inputs. We've looked at a pattern 8 inputs wide. We've just distributed things differently, correct? So over here, now, how many parameters would I have? So this yellow block is identical to this yellow, so these 4 yellow blocks are identical, right? Each yellow block is only looking at 2 inputs, so it's going to be 2D times N1, correct? So that's 2D times N1. This pink block, what's it looking at? 2N1, N2, right? Because it's looking at 2 of the pink blocks, right? This is N1 neurons in the first layer, right? And this upper block is going to look at 2, N2, N3, right? You see where the numbers are coming from, right? And so this is the actual number of units. This one, if I were not distributing it, the actual number is going to look something like that, which is much larger. Okay, because I'd be looking at 8 neurons in the first layer. See, consider the total number of neurons. The total number of neurons over here is going to be 4 times N1, right? Each of them connecting to 8, so 8D times 4 times N1. This is looking at 2 times N2, so 2N2 is connecting to 4N1, right? This is looking at N3 is connecting to 2 times N2 because I have 2 N2 bars. So the corresponding non-distributed network is going to have these many parameters. Which do you think is going to be larger? The one above, right? Because things are not being shared. They're not being reused. Yes?
Maybe this is a stupid question, but each 2 inputs represent 2 pixels and the 8 inputs represent the
This is, I'm looking at a time series, so this would be like speech, right? So the 2 inputs are going to be 2 spectral vectors. You can generalize this thing to, I'm using the one-dimensional example just for illustration, but you can generalize this to pretty much anything, right? And so the actual number of unique parameters are these guys. Those are the only unique parameters. The 2 sets of weights going down to the input, the 2 sets of weight going here, the 2 sets of weights going here. Those are the only unique parameters, right? That's what we are counting down here. And so when you compare these two, and the actual scan is going to look like this, right, as you go through the entire input. And this is the actual large network that's looking at the input. Okay. Now, all of these circle blocks, they are reusing computations that were done for scanning at a previous location. So there's a lot of reuse of computation that's happening, which means that the actual amount of compute you're going to perform is also going to be much smaller than if you simply scanned with a single network, because you're reusing computation, right? So now, here's another example. Can somebody take a shot at how many parameters this guy would require? For the first layer, how many parameters? There's K1, I'm calling this K1, right? So it's going to be K1D times N1, right? For this second layer, how many parameters? 2N1, N2, because things are being shared, right? And then the third one is going to be 3N2, N3, because again, all 3 are being fed in. And if I scanned with this, I'd still be reusing compute a whole lot. And I'd be saving a lot of computation. So if you actually look at the kinds of numbers that you end up with, I'm going to skip these slides because this is the same thing being explained for the 2D case. So I'll let you go through this in the slides. It's not so hard. But here's what happens. If I was scanning using a conventional MLP, in this particular example, I get 1034 parameters. But if I scan it using a distributed network, which is looking at the same number, same area, and is using the same number of neurons to analyze each location, I get 160 parameters. And the difference can actually be much larger. As the networks get larger, it can be several orders of magnitude. Right? So that is to answer your question. Why distribute? So why distribute? Distribution forces localized patterns in lower layers, so it's more generalizable. The number of parameters can be greatly shrunk. And the key intuition here is that regardless of the distribution, we can view the entire network as scanning the picture with an MLP. The only difference is the manner in which the parameters are shared across the MLP. Questions? Okay, for the next few slides, I'm going to fly through because I'm going to be doing at the usual rate of 50 per minute. So here's the story so far. Slide number 233. You didn't even realize, did you? So now position invariant pattern classification can be performed by scanning the input for a target pattern, and scanning is equivalent to composing a large network with shared subnets. The operations in scanning with a full network can be equivalently reordered as scanning the inputs with the individual neurons in the first layer to produce scanned maps of the input, jointly scanning the map of the outputs by all the neurons, or jointly scanning the maps by the outputs of all of the neurons, right? Because each neuron is going to be looking at the outputs of all of the neurons, and so on and so forth. And the scanning block, again, can be distributed over multiple layers of the network. This is what we've seen so far. Now, here's a different perspective. You can think of the entire operation before a scans of the entire image. You can say that the first neuron scans the entire input, like so, to produce a map. So each of the neurons would be scanning the input to produce a map. Then you can say that the neurons in the second layer are going to be looking at treating the maps, which are at the output of the first layer, jointly as one stack, and just scanning them to produce their own maps. But when these guys scan this one, they're effectively scanning a larger block within the original image, right? And the neuron in the next layer, again, they're going to be looking at these jointly, basically as a stack, and scanning them. And when they do so, they're actually scanning an even larger region of the input. This is how the whole thing goes. And so the first layer may be looking at subregions sufficient to say detect petals. The second layer will be looking at regions of the output of the first layer. So maybe put the petals together into a flower, something that looks like a part of a flower, then something that puts them all together to compose a whole flower, and so on. So each of the scanning neurons, we're going to call this a filter, to use signal processing terminology. It's really a correlation filter. It's really a correlation filter because you have a pattern of weights, you have a pattern of the input, you're taking an inner product. If I fix the magnitude, the length of these two weight vectors, the input vector and the weight vector, when is the inner product maximum? When they're both identical. So it's actually looking for patterns. The patterns are looking, your filters are looking for a pattern. So they're correlation filters. And the pattern of the input image that each filter sees is often called its receptive field. Now the receptive field for these first layer patterns is obvious because you just have to look at the weights. But when you try to begin looking at the receptive fields of these higher level neurons, it's more complex because they're looking at complex patterns, which are combinations of the inputs of the patterns detected by the first layer neurons. So they have to be computed. So typically, also when you learn the whole thing, you're not really going to get these nice, beautiful patterns like flowers and inflorescence and so on. You're really going to get something which is a lot more abstract when we learn these things. We'll see this in a couple of classes. And the final layer again can be fed into an MLP, which is exactly what we saw before. Now, some modifications, right? First, when I'm scanning, I don't need to scan 1 pixel at a time. So this is what we will call a stride. So if I'm scanning more than 1 pixel at a time, then basically I'm effectively increasing the granularity of the scan. And if I was scanning 1 pixel at a time, this map is going to be pretty much the same size as the original image. If I'm scanning 2 pixels at a time, it's going to be halved in size. If I'm stepping over 2 pixels at a time when I'm scanning, the output is going to be half the size, right? And you can do this at any layer in the network. You can just choose that at some layer in the network, I'm not going to look at it 1 pixel at a time. I'm going to begin jumping. And this should be fine. This will reduce the size of the map and reduce the amount of computation you're going to perform, right? So if you are actually going to write the pseudocode, when you're skipping, all you do is jump over a stride, right? Now, another thing we would like to do is to account for jitter. We want to account for some jitter in the first level patterns. Let's say I'm looking for something that looks like a petal, and I'm putting together the components of a petal, right? If one of those components shifts by a pixel, would you still call it a petal? Most likely yes, right? These little bits of jitter don't destroy the pattern, and you want to codify the fact that this little bit of jitter doesn't really destroy the pattern. So we will often do this by saying, I'm going to look in a small region, and remember what we did when we went all the way to the beginning and said, is there a flower in this image? You scanned the entire input, and then you took a max of all of the outputs, correct? And that told you if there was a flower or not. We're going to reuse the same idea all the way down to the bottom. So you're going to say each of these guys is looking for a small pattern, and it's okay for that pattern to move around a little bit in the region. And so you would say within each location, you're just going to pick the largest value in a region around the location and replace the value at that location by the largest value. You're taking the max. Yes, Stefano?
Since we usually use a stride greater than 1, if we want a deep network, we'll have to start padding at some point, right?
We'll get to that in the next class, yes.
Okay.
We won't always use a stride greater than 1, but yes, things will keep getting smaller and smaller, right? So this is what is called max filtering or max pooling. You're scanning it with a little block and picking the max in each location. But then what do we know about the max? The max is just an activation function, is it not? We've seen this in the class. So this is literally like just adding another layer to the network whose has no weights, and who just has the activation, whose weights are all 1, and the activation is a max. So so here's how the max would look, right? Within each location, you're going to be picking, say if I'm looking at this location, I have these values, I'll just be replacing that value with 6, which is the largest one. The max is just another neuron, as we see. So instead of applying an activation to the weighted sum of inputs, each neuron just computes the maximum over all of these inputs. But we know from previous classes that the max is also just a standard activation. This is just a standard neuron. And so you can redraw this. You can redraw the max operation as just another layer that immediately follows the previous activation layer. This has not changed the fact that the whole operation is still just one giant shared parameter network. Right? So, and because I'm scanning, I can still scan. Right? I can just do the same thing with a scan as before. Now, and often when you actually perform the max, you're not going to be stepping one pixel at a time, but you'd be jumping over groups of pixels. You'd have large strides. And so typically these max operations result in a shrinking of the map, something that's called downsampling, because you're reducing the size of the map, right? It's not uniform downsampling. You're picking the max within each region, but it's a downsampling. So, and then the subsequent higher layers work on these max pooled layers. And so the overall structure is going to look like this. In reality, you can have many layers of convolution, which is scanning, followed by max pooling, which often uses a stride greater than 1 to result in a reduction of the map. And in all of these, pretty much the individual perceptrons at any scanning or convolutional layer are just called filters. They filter the input to produce an output image. The individual max operations, just terminology in case you run into it, are called max pooling or max filters. So whenever we think of these scanning kind of networks, we talk of our perceptrons and neurons as filters, borrowing upon terminology that these electrical engineers like to use. So, and this entire structure is what is the popular convolutional neural network. Now, so if you ever wondered where this crazy CNN structure came from, there's very clear and distinct logic to it. What you're really doing is scanning for patterns and distributing the manner in which the patterns are represented across the network. You threw in a few more engineering tricks to sort of reduce the amount of work you do by subsampling or downsampling and things like that. But the whole thing is just scanning with a neural network. And all of this might look like magic, but if you think of the operation that's happening within any one block, that's a perfectly valid neural network where you have a bunch of neurons with shared parameters looking at the input, and then you have some layers which do some max pooling or something similar to sort of account for variations or jitter, right? So one of the very first instances of a network of this kind that was very successfully deployed was this guy here by Jan LeCun, who won the Turing Award last year, essentially for this figure, right? So you can trace his Turing Award back to this picture. Now, this was his implementation of a convolutional neural network. There was this task called the MNIST task, which is all of you are probably familiar with already, which is handwritten digits. And it turns out it's a fairly easy task, the way it's actually designed. They slice out the digits to make you classify them. And so people get 97, 98, 99% accuracy with things like k nearest neighbors. But then if you actually want to run your classifier on an envelope where these digits are handwritten and where you don't know where one digit ends and where the next one begins, then you run into a completely different issue, right? And that's when shift invariance begins to figure. And so Jan actually built this convolutional neural network. Here are the specs of it. The input was 32 cross 32. His first set of pixels, first set of neurons, looked at 5 cross 5 regions of the image. So remember, your filters are going to scan the network, but then they may or may not fall off the edge. If you don't want them to fall off the edge, the size of the output shrinks. So these are now 28 cross 28. Then you scan them with something else. 2 cross 2, you end up with 14 with a stride, end up with 14 cross 14. Then you scan them with something else, you get with. There's a whole sequence. We'll go through this in the next class, right? But the nice thing is he came up with this really nice demo which shows real-time classification of handwritten digits and the US Postal Services. actually used this little lay net for several years. Now, we have been talking in the context of images, but I can actually go back to the very first picture I showed you of any kind of signal, which was a speech signal, right? In that case, it's still the same thing. It's still a convolution, but now we're convolving only across time because their patterns are not moving up and down across frequency. We'll call this a 1D convolution, or this is also called a time delay neural network. And so you'd have this is a 1D scan version of the convolutional neural network. The representation would be the spectrographic time frequency components, and the computation is performed exactly as we saw in the beginning of the class. There's one key difference, that when we actually perform time delay neural networks, we don't account for things like jitter, so you don't have max pooling, because accounting for a little bit of jitter makes sense in images. A little bit of jitter can completely change the phoneme that you're trying to pronounce in speech, and so you wouldn't actually have max pooling in time delay neural networks. So this whole thing is a TDNN, right? So we are sort of done with today's lecture, right on time. Here's the story that we've gone through. First, we went through 281 slides. But what we found is that neural networks learn patterns in a hierarchical manner, simple to complex. Pattern classification tasks such as, does this picture contain a cat, are best performed by scanning for the target pattern. Scanning for patterns can be viewed as classification with a large shared parameter network. And scanning an input with a network and combining the outcomes with outcomes is equivalent to scanning with I'm not sure exactly what I'm trying to say here, but I know what I'm trying to say. I'm not sure how I've said it. The point is you can change the order of the computation, and the result is still going to be the same, right? And each scanned block of the input can be distributed over multiple layers for efficiency and for better generalizability, because you're going to have fewer parameters and you're going to be able to learn things more robustly. At each layer, a scan by a neuron may optionally be followed by a max or any other kind of pooling operation. We'll see a few more in the next class, not Wednesday, but on the Monday following. And for 2D or higher dimensional scans, the structure is called a convolutional network. If you're scanning along only one dimension, even though the input is two-dimensional, right? Then we will call this a time delay neural network. So I'll stop right here. Do we have any questions? No? We're done. See you on Wednesday.